So the idea of the talk is to talk a bit about tensor networks. And tensor networks is just a mathematical structure to describe families of vectors in tensor product spaces, or in spaces of the form CD, tensor CD. Okay. And the nice features is that, first of all, they allow to use quantum information ideas and techniques. And second, that they keep appearing and having impact in several areas. So the goal of the talk is to introduce them and sketch some of these applications or why they are interesting. First, in quantum many-body problems, where the origin can be traced back to. And at the end, also in other areas, like in quantum computing, okay, in holography, but this, I don't know much, so I will just sketch things in information theory and in numerical analysis. That's a bit the idea. Okay, so, okay, let me keep like that, horizontal. Okay, so, as I said, the origin comes from the quantum many-body problem. And essentially, they're like, starts probably with the famous AKLT paper, Alfred Kennedy and Tasaki, which they describe a particular Hamiltonian, which is the AKLT Hamiltonian, who has nice properties and as a proxy to the antiferromagnetic Heisenberg model. And this is in the late 80s. And then two papers by Fanes, Nachtergaele, and Werner in 92, in which they define properly the first and most important class maybe of tensor networks, which is matrix product states. Matrix product states. And then Steve White, DMRG method, also 92, 93, in which essentially he designs an algorithm to approximate the ground state of a one-dimensional Hamiltonian by optimizing on the family of matrix product states. So that's a bit the origin. And then I will first, so the span of the talk is, define objects, define. Then some use in quantum many-body, and then use in other areas, like in quantum computing, information theory, quantum computing, information theory, holography, etc. Okay, that's the plan. Okay? Good, so, okay, so let's go into business and define, so point one. And define the objects. Okay, maybe let me do this in a more, let's put here dots. Okay. Okay, so the best way to define tensor networks so that you can use them beyond one dimension is to define a graphical notation. So a tensor T is just a sequence of complex numbers. All these are complex numbers. And therefore is an element simply in C D1 tensor C D2 tensor C DL. Okay, so that's what it is. Yeah, yes, I will. Sorry. Let me find.
Please move forward so that you can see the.
In any case, I will use it, but.
Yeah, there are plenty of spaces here in the front.
Okay, so a tensor T is just T of I1, I2, IL. I1 runs from 1 to D1. IL runs from 1 to the L. All these elements are complex. It's just simply a bunch of complex numbers with a multiple subindex, and therefore T simply is an element of CD1 tensor, CD2 tensor, CD. Okay? And now the notation, I will define what's called the box leg notation. So to this one leg per index. Okay, so for instance, this leg will be associated to the index D1, so this leg corresponds to C of D1, maybe this C of D3. Okay, so this is leg 1, 2, 3, 4, etc. Okay. Okay, so that's the notation. Simply when they write T in a box with many legs, this simply means a tensor whose coefficients are T sub whatever. Okay. Now when I have this notation, I need two main operations. Now let me see if I'm able to. Okay. Two main operations. Operation 1 is tensor product or Kronecker product. Product, which is simply T tensor S, is the tensor T of I1, IL, S of J1, JK, I1, IL, J1, JK, where of course T is this tensor and S is this tensor. So simply what I do is I put all the possible product of all possible coefficients, and now I have many more labels. Okay. So, oops, see if I'm able to do this like that. Okay. So this if T is T of I1, IL, and S is S of G1, JK. Okay. Okay, so just simply do that. And the graphical notation is just putting the two tensors together. This is the graphical notation for this operation, for the tensor product. Okay, simply I put the two tensors together. That's it. So that's the graphical notation. Is just you have T and S. This is TDSF. If I put the two things together in the blackboard, this simply means tensor product. Okay, and the second operation is tensor contraction. Okay, so if I have a tensor T, and I would like to contract, so T, of course, I don't write it anymore. Okay, once more, but T of I1, I2, IL in such a way that D1 is equal to D2. Then the contraction of legs 1 and 2 on T, let me call this T hat for simplicity. This is just the sum in the variable associated to 1 and 2. Then in these variables, I identify the two indices, I1 and I2. I identify them, I put II, and I sum over that. It's because of that I need that D1 is equal to D2. And the rest of the indices are left invariant, I mean just untouched. And this, sorry, I3, excuse me. These run from I3, I4, IL. From 1 to D3, D4, DL, respectively, okay? Okay, so essentially what I do is I identify index 1 and 2 and sum over that. And the rest are untouched. Okay, so that's tensor contraction. So this is just simply doing, okay, we'll write it here. So this is simply doing say the operation, duality operation on 1 and 2, tensor identity in 3L. This is identity. Okay, and this operation is simply the duality transformation. Because it's simply, okay, this is just if I have two elements in the computational basis, this is just the delta function. Okay. So this is mathematically this operation of contracting 1 and 2 is doing the identity in the rest of the indices, so the identity in this part of the CD, and in the other, I do this other operation, okay? And the notation for this is just, if I have T, I have, this is leg 1, leg 2, leg 3, leg 4, etc. What I do here is the two legs associated to the two indices I want to contract, I simply join the two legs. Like that. Okay, that's the notation. Okay, any question about these two? These are essentially the two only operations I will need. Yes? Okay, good. Okay, so let's do some examples. Now I need to use this. Okay. Okay, so let's do some examples. So let's start with the simplest thing, which is one leg tensors. So, okay, something like that. Width, of course, is just a vector, vi from 1 to d. So now, if I have some vector, I have a vector w, then I can define W bar, which is simply J. This, and the bar means the complex conjugate. Complex conjugate. Okay. And now, as an exercise, let's do what does it mean to do this thing. Okay, let's see how to compute this by using the two operations I just defined as a warm-up to get something much more complicated later. Okay, so what do we need to do that? Okay, so then first, we plug the two tensors here, okay? So this is, so as I say, the goal is to compute this object. This is some tensor object. So the way to compute that is first, I do that. So this is just the first operation, which is tensor product. As I say, the notation is to put the two tensors together. So this object is just Vi Wj I from 1 to d, j from 1 to d. Okay? And now second, I join the two indices. Okay? And now look what I have to do. Now I have a tensor here with two legs, these two. And I have to identify the indices and sum over that. So this is just summing I from 1 to d, w vi, or the opposite, okay, it's the same. To keep the, okay? Which is just the scalar product. Okay? Of W and B. Okay, so this is. Okay, so let's do now second example, which is a bit less trivial. Instead of doing one-leg tensors, I will do two-leg tensors. Again, let's put it here. Again, scalar product. Two-leg tensors. Okay, now I have a two-leg tensor like that. This is just Aij, so Ij from 1 to d, let's say. It's an element in CD, tensor CD. Okay? And this, of course, is just a matrix. No? This is a tensor with two indices is just a matrix. So this is just a matrix. Can be in general as a rectangular matrix, but for simplicity, let me consider that both indices have the same dimension. So it's just a square matrix. Now, if I have two matrices A and B, if I have another matrix B, okay, L, I would like to know what is this object. Second exercise, to see how to compute this object, again, using only the two operations of tensor product and tensor contraction that I define. Okay, so let's do that again. First, I put the two tensors together, like that. And this is just Aij B times B KL Ij KL from 1 to d. So put the tensor. And then second, let me call this leg the one associated to I, associated to J, to K, and to L. And then what I would like to do then is to contract that to be, okay? And what I have to do is, the two indices I'm contracting is this with that. So this is the one of J here and K here. So I have to identify and sum over them. So this is just the sum J from 1 to D, A, I, J, B, J, L, I and L from 1 to D. Okay, and that's exactly matrix multiplication, no? Because what I'm doing is I'm identifying the column index of the first matrix with the row index of the second matrix and sum over that. And I recover another matrix, as it should be, because this is a tensor with two legs, 1 and 2.
David,
Yeah.
I think you can safely assume that people know this.
People know these things. Okay, sorry about that then.
The notation.
Perfect. So this is matrix multiplication. Thank you. Thank you. Okay, good. Okay, let me go faster then. Okay, so thank you. Sorry about that. Okay, so with this notation, then what I can do then is to define families of tensor networks that are of use. Okay, so let me do that now. Okay, so now I have to bring this back. Okay. This is not so obvious. Oh, okay, good. So, okay, good. So, okay, so now let's go to our first family of tensor networks, which is matrix protestates.
You also assume that people know this.
Okay. Also, PEPS. People know all possible tensor networks, but the most famous ones, yes. Okay, matrix protestates are simply with this graphical notation, objects like that. If I assume that all matrices are the same, that I will do most of the time, I call this psi A, and this is a matrix protestate. Okay. Okay. Why are matrix protestates useful? Well, first of all, interesting, and the reason is that okay, these are MPS, and then PEPS. Let me define PEPS. They are defined by a 5-leg tensor. And then this is okay, object like that. And again, if the usually consider periodic boundary conditions. Okay, like that. Okay, good. Why are these objects interesting? And the reason is that essentially matrix protestates and in general PEPS, so this is just for one dimension, and PEPS for higher dimension to D and higher, they essentially correspond to the set of ground states of gapped locally interacting Hamiltonians. Okay? So what is known about that? So look that in order to say that this set is equal essentially to this set, I have to give like two containments. So first of all, there are some theorems that I will state kind of the state of the art that tell that ground state of essentially this containment up to epsilon. So the set of ground state of gap locally interacting Hamiltonians is a subset up to errors epsilon of the set of PEPS and MPS is relevant because these tell us that in order to parameterize these objects that are one of the main central objects of interest in quantum many-body problems, is enough to consider states of this form or of this form in higher dimension. Okay, so theorem, the question essentially, the question is if I have here the basic tensor A, I have here this corresponds to CD, and that's what is called the physical index. And this corresponds to C capital D, and this is the virtual, capital D is the virtual dimension. And the same here, this is CD and the others are CD, capital D. So the question is how large D needs to be to approximate, well, up to epsilon ground states of gapped Hamiltonians. Okay, so the question is which is the function that depends on the system size and the error, no? Where L is the system size, and the same here. Okay, assuming this is L times L. Okay. Okay, so what is known? So let me just state properly. This is via Arat et al. This says that, okay, if we take D, okay, and this is for the case of, okay, which, okay, I will say that. E to the order, if we take D, E to the order log 3/4 of L over gamma, then the error is 1 over poly L. Okay, and this is sublinear. Okay, gamma is the gap of the Hamiltonian, and this is sublinear. This. Sorry? Oh, okay, sorry. Thank you. Okay, maybe it's yellow. Okay, this is the gap. And this is a sublinear growth. okay? Because it's e to the log and the power is less than 1. Okay, a note is that this works for the case in which these tensors can depend on the side, so A1, A2, A3, AN, okay? So in this theorem, the A's are allowed to be depending on the side. But this tells us that if you have a Hamiltonian with a gap, then with a bond dimension that is sublinear with the system size, the error can simply go to 0 with the system size. Okay, good. I mean, I think the question is that, so what one can prove is that if essentially you only care to approximate I mean, it's a good question. Maybe it's a good question for discussion. But in the positive side, what I mean, probably one. Epsilon is the L2 distance with the ground state itself. I mean, and then. Exactly. This is what I'm going to say. That if you only care about relational invariant Hamiltonians, and you only care about expectation values of observables, essentially of rank R, essentially Ors, then this only depends, is independent of L. But depends, however, on the size of the rank of the observable you want to compute. And this is a simple corollary of this. That's indeed a one-page proof that by Norbert and Frank. But exactly, so maybe this. So let me state if you want the corollary. Sorry? Yeah, yes.
What's the scale of gamma?
Is the
Doesn't depend on how you normalize the gamma.
yes, but I mean once you, I mean this is about the scaling, no, with O, and then this is once you have the, I mean okay. So you fix the Hamiltonian first, and once the Hamiltonian, I mean you take like a traditional Hamiltonian, you first fix the Hamiltonian, and then change the system size. Once you fix the local term in the Hamiltonian, okay, you can multiply by something or divide it by something, but this is just a constant, I mean, that adds on.
So that's it. The local term that will have as mode 1. Okay, that answers this question.
Yes.
But then comes the second question. Now you look at the number of ground states. Nearly ground states. Then there is a gap. For example, the sequence of and is this gamma the difference between two almost ground states, or do you think the gap between another states?
Okay, in this case, I think they do have also more recent. I mean, I think in the resultant commenting here, I think this is just for a single ground state, but there are more recent papers in which they managed to cover that case, in which even, okay, probably depends on how many ground states you have, no? Because I mean, this is, I mean, if you have exponentially many ground states, essentially, probably the question if there exists at least one with a small bond dimension, because otherwise you have many. I think that, again, probably should check the reference, but there is a more recent paper by some of the authors here and other, in which they cover that case up to some extent. Essentially, they managed to prove good bounds as long as the number of ground states, or essentially small energy states, is not that big, like logarithm or something like that. But I can give you the exact result. Maybe.
Yeah, it's for poly.
Even for poly. Okay.
You mentioned the spatial dimensionality field. Have you talked about MPS?
Yes. This is for one dimension. Yes, 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 yes. This is for 1D. Yes, I will tell you which is the 1D. Okay. More questions? Yeah, please.
Is there a lower bound on what D has to be?
Sorry, yeah?
Is there a lower bound on what D has to be?
I think, yeah, it's same question that before. So I don't know which is.
Which has D equals 2.
Oh, well, of course, yeah, but the question probably is whether there is a bound that grows with the system size.
D is 1, and maybe just logarithmic of 1.
Exactly.
1 over gamma.
No, but for the EKLT it's constant, so there cannot be a general one. No? For the EKLT, all dimensions equal to 2 is
Yes.
constant independent of the system size, so it cannot be a lower bound that works for all, including EKLT.
No, I don't know which is the exact question is whether there is, I mean, so examples that, I mean, show that this bound, that this sublinear cannot be like logarithm or something like that, right? No. Lower one. Yes.
But Kumac, I remember in the area law paper, you say the bound is basically tight. You get a 1 over delta to the 4 for the area law or something like that. That's basically right.
Well, you know, the interesting thing for us was the dependence on little d. The interesting thing for us was the dependence on little d. You know, the external, you know, the dimensions of each physical. And there the dependence is e to the order log squared little d. And if you could improve that, you know, even slightly, you would get 2D chemicals.
But still, I remember there was a comment that the gap scaling couldn't be improved much more because there were examples with that gap scaling. Right?
Sorry, yes. You mean this?
Also do the scaling.
Only one of them. So, or it was. The gap. That's what you carry out. The gap. So the question how it's going to say, I don't know. I mean, that would work.
As far as I know, there are not much lower bounds, but of course, probably, yeah, it's interesting, as you say, which is the scaling both on gamma, L, epsilon, etc. Probably you fix one, yeah, I don't know. But again, maybe it's a good question for the discussion to see, to give examples at least that optimize one of the parameters. I guess for the gap, yeah, probably better than 1 over poly is probably not possible, but okay. Sorry, I cannot tell much more. Okay, so which is the case for 2D? Okay, so here, okay, I think I don't have here written the exact dependency on the gap, unfortunately. So I think this result is from Andras, Norbert, Ignacio, probably someone else that I forgot. Frank? Sorry, Frank. So, and the result that improves on previous result by Matt Hastings essentially is that for a constant gap, and I think the gap is also in the exponent, but I don't know in which, I didn't write it. Constant gap. But also there's another hypothesis, which is that there are not, so that the ground states with the system size don't accumulate, that eigenstates don't accumulate in low energy with the system size very bad. So essentially that for a fixed k, for any k, the number of eigenstates of energy less or equal than k grows only, or at most, poly, at most, or grows O poly L. Okay. So with these two hypotheses, the scaling, okay, I can give here maybe the scaling. With these two hypotheses, the scaling D is E to the O log square L over epsilon. No, gamma is somewhere in the exponent. So I'm sure it's in the exponent. So it's really, I mean, it's log that over gamma, but I don't know if it's gamma or gamma square now. I don't know if some of the authors can tell, but it's definitely in the exponent.
I don't think you need that gamma, no. I think the eigenstate assumption is enough.
Really?
Yes.
Oh, okay.
The philosophy is that you take a temperature which is logarithmic in the system size, and then if you have a low density of states, you're very likely that quantity.
And this is
It's just that for gapless systems, this condition is typically violated.
okay.
That's why it's not reasonable.
Okay, good, good, good. Okay, so then there is no gap because there is no need for a gap. Okay. Well, I thought it was needed, but maybe I'm wrong. Okay, good. Good. Definitely you know better. Yeah.
No intuition whatsoever. Is this assumption holds in many known systems?
I don't think we have a single gap example which violates this,
Yes.
except for examples which are kind of wrong because they have a system size dependence in parameters.
Yeah. But on the other hand, it's very hard to prove this property. I mean, proving the gap already is very hard. So this is even harder. So things like classical systems, maybe you can prove it, but
So when you say you know it, but no meaning.
Okay, as a physicist, I would say you have a system which only has particle-like excitations and a gap, then this will hold. No, I'm not sure how that's
What's in the lab?
Sorry?
What's in the lab? or
When
what's
it's
in
not a
that?
series. But that's not a proof, right? No.
okay. Yeah. So as I said, even the gap is, I mean, gap is extremely hard to prove also. I mean, so this is even harder. So I mean, it's not really that many systems one can really prove these things. Okay, so this is what covers somehow the state of the art essentially about why or in which sense PEPS or MPS approximate ground state of gap locally Hamiltonians. There is also a nice thing, which is the reverse implication, which is that all those objects are also ground states of particular Hamiltonians. That's also nice. So let me. Yes. What? Sorry? I mean, it's just. I think so, yes. No, but this is how it grows with L. So you fix first K and then grow L.
The exponent is k, it's like L to the k or L to the k.
Yeah, yes. Of course, yes. I mean, the polynomial can depend on K. Yes. This for fixed K, then yes, definitely yes. Okay. Good. So for the other side of the question, let me try to see how. Oh, sorry. Let me push this. Okay, so Okay, so for the other implication, so essentially there is a construction which is called the Pérez-Hamiltonian construction. So essentially one can prove that MPS and PEPS in general are a subset of the set of ground states of local Hamiltonians. And for that, there is something which is called the Pérez-Hamiltonian construction. And for that, somehow one needs to see, imagine they have a PEPS. Etc. And then I consider a region in the PEPS, for instance, like this particular region. And if I zoom there, 3, 2. So this object can be seen as a map. This is a tensor from with essentially the boundary of the region R, so that's the region R, times the bulk of the region R. And therefore I can see this as a linear map. This is a linear map. Gamma, that depends on the region, from the virtual to the physical one. Okay? And essentially, so this can be seen also, if you want, the transpose map that goes from the bulk to the boundary. And indeed, this is usually what is used. So if you can see this as a linear map like that, or the transpose map, or there's a linear map, or it's also a linear map. Let's call B from the bulk to the boundary, which is just a transpose. Okay? So this defines these two maps. And then, so in this case, in which we have a lattice in the plane, indeed, the interesting one is the one from boundary to bulk. But if this is in hyperbolic geometry, somehow the bulk is smaller than the boundary. And then this is the interesting one. That's the one that appears in these holographic toy models, like this happy code, etc. That show that if this tensor is nice, it's like one of these perfect tensors, then, and we have an hyperbolic geometry, this object is also an isometry, and these holographic codes can be seen really as codes. I mean, as isometries from a small subspace into a bigger subspace, and therefore they can be seen as linear codes. So that's the one that this is the one that's interesting in holography, but for hyperbolic geometries. So not for this plane one. Okay, but here we will care about this one here. And then the Hamiltonian. The Pérez-Hamiltonian is very simple. Simply, we take the range of gamma. That is the set of all elements I can create in the bulk by acting with a boundary condition. I call this G. And then the Hamiltonian H, the term of the Hamiltonian associated to region R, is just the projection, the orthogonal projection, or the projection onto the orthogonal of gamma R. Essentially, what the Hamiltonian does, it annihilates every element I can create in that region by acting with a boundary condition. And now if I sum over all translations, this HR, I get a Hamiltonian that is semi-definite positive because it's a sum of orthogonal projections, and that in the given PEPS is 0, and therefore the PEPS is a ground state of H. And this is called the Hamiltonian construction. And there's some hypotheses on the PEPS, some we call injective, Wyckoff injective, G injective, several hypotheses. One can prove that indeed the given PEPS is the unique ground state of the Hamiltonian, or unique up to some well-controlled topological degeneracy. Okay, so under some hypotheses, this is a very good question. So
far, it's all regions R.
So far, no, yeah, okay, but one has to pick up properly the region R. That's a bit the question. Yeah, yes. In principle, this works for every region R you want, and this is true. The problem is you could have many more ground states. So if the region is very small, big enough so to guarantee that the ground state, the PEPS, is the unique ground state or unique up to topological degeneracy, and that's what gives you a size of the region. Because okay, I mean, of course, if I take the Hamiltonian equal to 0, all this is true. But of course, it's not very useful, right? So essentially, so there are some conditions. For instance, the simple one is what is called injectivity. And injectivity simply means that the linear map gamma is injective, okay? As a linear map. So if R is essentially the size at which gamma is injective plus 1, this is enough to guarantee that the ground state is unique. So this guarantees a unique ground state. Okay, if instead of R we take R plus 1, okay, but whatever. I mean, essentially R gives you the size at which the ground state is unique. But of course, it could be that even if you grow R, okay, and that for some R, gamma R is injective, this is generic. This is not difficult to see by counting dimension. Okay, one can prove it. But because the dimension of the initial space grows with the boundary, and the dimension of the image space grows with the volume, and therefore, when we increase R, this grows much faster than that. So essentially, generically, one expects that at some point this becomes injective. But there are examples of PEPs, especially those having topological order, for which this is never injective. And the reason is that precisely for states with topological order, we cannot expect a unique ground state because we should expect degeneracies. But still, there are generalizations of this notion, which is called G injective, H injective, whatever. That work similarly for systems with topological order. And in this case, the ground state is not just unique, it's unique up to the topological degeneracy of the model. Yes?
The way you define the Hamiltonian, maybe it's easy, but I don't see why it's a local.
Oh, yeah, good. Sorry. We fix R. Let me fix R. So I define the local term HR And I see, oh, sorry. And I sum on the translations of that. So it's a finite range. So all the terms are finite range.
It's not local on the board, it's local on the region.
Exactly. You have a finite range interaction. So it's.
So there is some mismatch between the containment in this direction.
Yes. Okay. This is again. So in this direction, no, it's also okay. No, I mean the type of Hamiltonians I'm considering is also similar. They are finite range. So there are sum of terms, and each term act only on a finite size.
So that's the definition.
That's the definition of finite range. One can also to take tails that decays exponentially or something, but for finite range, this is the definition. You take interactions that act on, let's say, plaquettes or something bigger, but let's say plaquettes, and then you sum on all possible plaquettes.
Don't see the play between the locality and the globality. And if the system is infinite, okay, it's finite range. But if it's a finite grid, I want to know what is R as a function of A.
Yes, exactly. Okay, so there are not known bounds on which is how big. So the only case in which results in this direction are known with concrete bounds is in one dimension. So in one dimension is known that if at some point gamma R becomes injective, this R must be smaller than the bond dimension squared times log the bond dimension. So there is a bound that only depends on the bond dimension. In higher dimension, it is known that there is a bound that only depends on the bond dimension, but in principle, this bound a priori could be even uncomputable as a function of the bond dimension. But there is a bound also that depends only on the bond dimension. Yes. Yeah. It's a very good question, and in general, it's not. So in one dimension, it is always gapped. In two dimensions, there are examples in which it's gapless, and there is a very simple reason, because there are some PEPs with bond dimension 2, we have power law decaying correlations. So of course, they cannot be never unique non-state of gap Hamiltonians. There are some characterizations of the gap based on something which is called the boundary state that allow to work, I mean, give even bounds that are interesting for the lifetime of quantum memories. I can tell you in a second. But in general, it's a very hard problem. Indeed, for PEPs, given a PEPs, to know if the parent Hamiltonian is gapped or not is undecidable. So indeed, there cannot be any algorithm that tells you, given the tensor of a PEPs, whether the parent Hamiltonian is gapped or not.
So this is a feature, a cool feature, because the network can also simulate some captures to say, or
yeah. No, I mean, it simply says that in all these containments, there are subtleties. And the subtlety here is that I didn't write gap, because to include the gap here, you need something else here. So for instance, let me tell, so there's this result. So again, there is some sort of a nice kind of holographic duality in PEPs between the bulk and so the PEPs itself and what is called the boundary state. The boundary state is simply, so given a region, I define the boundary state, say the boundary state of the region as gamma R da. This is called the boundary state of region R. And if you look at what this is a mixed, okay, this is obviously a semi-definite positive operator. So it's a mixed state, maybe not normalized mixed state, a mixed state living at the boundary, at the virtual boundary of the region R. And then somehow there is a bulk boundary dictionary. So there is this conjecture with some numerical evidence by Ignacio, Didier Paul-Blanc, Frank, Norbert, I don't know who else, maybe someone else, that tells essentially that the parent Hamiltonian is gapped if and only if this boundary state can be written as, from the boundary state I define the boundary Hamiltonian, and this boundary Hamiltonian is somehow local. So the locality of the boundary Hamiltonian corresponds to the gap of the bulk. So, and okay, we proved, okay, some years ago that one implication is true, so that if this boundary Hamiltonian is local, the bulk Hamiltonian is gapped. So this is proven. So this is a conjecture, and this is proven.
The original Hamiltonian in the system is local?
No. Oh yeah, sure. No, this is the parent Hamiltonian. The parent Hamiltonian is always local.
Oh, we're only talking about.
This is about this is about the parent Hamiltonian. The question came from there.
Only about parent.
Exactly. This is about the parent Hamiltonian. Yes. So exactly. So essentially, and using that, somehow we have managed to prove that some particular interesting parent Hamiltonians, which are corresponding to the, if you take a topological model, which is a normalization fixed point, like Kitaev quantum double models, and fix a temperature, and you consider the thermofield double, so essentially the purified state, we can prove using this that the bulk Hamiltonian is gapped for every temperature by proving that the boundary state is local. And this is interesting because this gives a bound on the lifetime of the quantum memory associated to that object under the noise given by temperature, essentially. So this is a nice theoretical characterization, nice kind of holographic characterization from bulk to boundary, but it's also useful to compute in some cases. Yes?
Is that for fixed R, or is it for R that becomes R?
No, of course, this is for growing R, because of course, yeah, what matters is how the locality of H goes with the size of R. So this is for growing Rs, yes. This
The bulk Hamiltonian being gapped and also becomes for a single fixed R.
No, exactly. The gap is for, essentially the R that for which this is the same injective. Okay, so the parent Hamiltonian is fixed. Once you fix the parent Hamiltonian, in order to see whether it's gapped or not, you start try to understand how, with growing the region, how this becomes, the tails decay with that region, essentially. And once you have this, if you have this, you can prove the gap for the original parent Hamiltonian. No, it's, you are allowed to some tails, yes. Indeed, what we can prove is if the tails decay faster than exponential. For exponential, is it's not obvious.
Yeah, I'm not. We're going so there.
Yes.
Sorry. So there you're saying like you because you enlarge the R, you will change the definition of edge, right?
Yes.
Okay. So that's then it's like you fix the R such that it's injective.
No. Okay, there are two R's. Sorry, the notation is not very good. So I fix one R for which this gamma R is injective. This defines for me the interaction length of my parent Hamiltonian, and this R is fixed. Now this is a different R, and now take R tildes, growing ones, and for those, I try to see how the entanglement Hamiltonian locality goes as this R tilde grows. Okay, and if I have a bound like that, then I can prove that the original parent Hamiltonian for this R is gapped. But this R is fixed. Yeah?
I'm confused about this field. Can you state it?
Sure.
Quantify that. What is the field?
Yes, sure. Yes. Sure. I can tell you. Yeah, definitely. Yeah. Okay, so.
I think he wrote conjecture, right?
Yeah, sure. No, the conjecture. No. Theorem is only the implication from here to here.
Oh, the theorem goes one way.
So, and the other is only still conjecture. Yes. So, sure. Okay, so I have to define. I have to define the following quantity. Okay, the thing is I have. Okay, so. Okay, so. Let's assume that for a region of size, essentially regions of size L, okay, small l, the boundary state is e to the minus h. This depends on L, where h of L is a sum, and this is true for all L. It's a sum of all x contained in the boundary. So now HL lives in C capital D tensor 4L. Okay, because this lives on the boundary. Okay, so goes from here to itself. And now imagine that I can is the sum of all subsets of this, no, of the set from 1 to 4L of some interaction h of x in such a way that the norm of hx decreases essentially, let's say, e to the minus faster than exponential with the size of x. Essentially, I think it's probably enough. Let me check what is enough. I think e to the minus, okay, essentially size of x square with some alpha. Okay, so the norm decreases on a constant that independent of x. Then the norm decreases faster than exponential with the size, with the diameter of x. Sorry, diameter of x. Okay. Good. Now this constant is constant. So both c and alpha are constants. Okay. So if this is the case, then and this quantifies the locality in the sense that if x is very big, the norm is very small, essentially. If this is the case, then the parent Hamiltonian is gapped. This implies is gapped.
Hamiltonian is just a bigger grid.
The parent Hamiltonian is the definition I gave when the R I took is the one that comes from this gamma R being injective. So it's the interaction length of the parent Hamiltonian is fixed. But still I have to prove this for all L, this scaling for all L. Okay, and then I think, okay, the bound can be better than this one because it's enough that it's faster than exponential in a weaker sense than that. Definitely 1 plus epsilon is enough, but even weaker, I think, is enough. But this Gaussian decay is the one that we observed, we can prove for these topological models at finite temperature. That's why it's the relevant one. Okay. Okay, bye. Okay, so good. Okay, all this was a detour coming from the gap of the parent Hamiltonian. Okay, in any case, so let me sketch then some other. Okay, so essentially this is all I wanted to say, even much more than that, for this equality between MPS and PEPS being ground state of local interacting Hamiltonians. And as you say, I said there are several subtleties. The gap of this parent Hamiltonian in principle is undecidable. In order to have sufficient conditions to prove the gap, okay, so far the best we have depend on this kind of locality of the boundary state, and therefore this shows the importance of this boundary bulk correspondence in PEPS. Okay, and then, okay, and as I said, this can be proven. This condition holds for thermophile doubles of topologically ordered systems at finite temperature. At any finite temperature in 2D. Yeah, for RG fixed points, yes. No, sure, RG fixed points, definitely. So commuting Hamiltonians, yes. Okay, so how do we deal with topological order in 2D? Because I kept talking about things with topological order when I talk about the lack of injectivity. Here again, the motivation to compute these things was also to understand how temperature affects topological order, etc. Then the nice, I mean, why this is useful in PEPS to understand topological order is because there is a nice way. Okay, we see characterization, but okay, it's not really a characterization in the mathematical sense. Or at least not complete so far, of topological order with PEPS. Essentially, all known two-dimensional in 2D. All known two-dimensional models with topological order that are non-chiral are essentially modifications of Kita F quantum double models or string nets. Or string nets states. Among those, the quantum double models are simpler because the topological order of Kita F, because the topological order comes from a group. So there is a group, finite group, somehow, which explains the topological order, and then one doesn't need to deal with fusion categories or Wyhoff algebras and can work with groups. And essentially, the characterization is just a symmetry in the tensor. Essentially, I have my tensor, and I have an action of the group. Well, no, this is a very bad color. An action of the group that leaves the tensor invariant. Essentially, if I look from above, this simply means that there is some group action that leaves the tensor invariant. If one needs to or wants to go beyond groups, then this is no longer a tensor product action, but a matrix product operator action. So in general, this is a matrix product operator action. But okay, for simplicity here, let me consider this a group action. And let's see, just very briefly, why this symmetry, just this symmetry, can be responsible for topological order. And the idea is just to consider a non-local loop of those symmetries. Essentially, imagine I act with the symmetries here. Look that this is G, G inverse, G inverse G. So I can pass this to the other side by changing G by J inverse and all that. But essentially what I have is that this is equal to this, right? Just simply passing one to the other side. So then what I can do is to use this to deform this. So for instance, I can take this patch here and apply this. And then this disappears from here and appears here, here, and here. I can do the same now with these two. And then these maps here and here. Okay? So essentially, the string I had at the beginning here can be deformed, but can never disappear. So I can deform it, I can move it. If I keep deforming, I can move it. But this string, okay, this again, I consider periboundary condition. This is a string around the torus. Okay? So essentially, I can deform this string, but I cannot make it disappear. Because I can deform it, this string it cannot be seen by any local operation, in the sense that if I consider a local operation acting somehow in a region, here, in principle, the string is there. But because I can move the string, I can take the string and push it far away from that region. And therefore, in this region, having the string or not having it, you cannot see. So this means that there are states which are the original PEPs in which I plug this non-contractible loop that locally behave the same. And in particular, this local operation can be the Hamiltonian itself. So these objects are also ground states. And okay, one can show that in some cases, under some of these strings, they are orthogonal ground states. So, but the idea is that essentially these kind of local observables do not see the string because I can move it far away. Okay? And then, essentially, this gives different ground states because, of course, this local observable, again, can be the Hamiltonian itself, different ground states which are locally the same. So that the reduced density matrix of each local region is exactly the same. And therefore, there cannot be any local order parameter, precisely because all these different ground states cannot be detected locally. And this absence of local order parameters is kind of, you want the definition of topological order. And so the reason behind that in the PEPS picture is simply this gauge symmetry. And then just playing with that, and of course, for particular cases that one can prove rigorously all these things I just said here, which are essentially these normalization fixed points or close to them, one can recover all the nice features of topological order, like different ground states which are locally the same. One can also understand the excitations as open strings, etc. So that's why PEPS is well suited to deal with topological order, and why I was talking all the time about things like this one, no? Things of topological order resistance. The things we are using here are these nice characterizations based on gauge symmetries. And so how this is kind of extends the things that were talked by Frank the very first day about how in 1D one can study symmetry topological order by also symmetries on the matrix product state tensor. So here one can do the same for normal topological order, also by understanding symmetries in the tensor. And the nice thing is that by understanding the symmetries in the tensor, it seems that is there where the global property of interest is locally encoded. So, and the local encoding here is this type of local symmetry. So that's okay. So in these last 5 minutes, let me super fast sketch applications of tensor networks to other fields. And for that, let me, for instance, bring this back. So for instance, regarding quantum computing, I already commented. Of course, these topologically ordered models are nice quantum memories. And indeed, estimating the lifetime of quantum memories of topological quantum memories is the same as understanding the gap of parent Hamiltonian. Essentially, gap of parent Hamiltonian of this thermofield double I considered before. So a purification of the thermal state. Another nice thing, even within quantum many-body, is that I didn't comment is about the parent Hamiltonian is that sometimes you have a state that is interesting, but you don't know any Hamiltonian. If you can prove that this state is a PEPS, immediately you can, I mean, it comes with a Hamiltonian. And this is the case for resonating valence bond state, for instance, that was defined as a state by Anderson in '73 and became more popular later when he proposed this as a mechanism for high-T superconductivity, but there was no Hamiltonian known for it. This is a PEPS, and as a PEPS, immediately we managed to prove a parent Hamiltonian, and we could prove that it has the nice injectivity conditions, so that this is unique up to topological degeneracy. So again, sometimes, I mean, there are nice implications even within quantum many-body. In quantum, so this was a parenthesis, I forgot. In quantum computing also, measurement-based quantum computation is a way of doing quantum computation in which one constructs a particular state, which is the cluster state. It's a state in 2D. And you start to do measurements sequentially, one after the other, locally. The measurements you do depend on the circuit you want to implement, the quantum circuit, and in the end, you can do every quantum computation like that by constructing an initial quantum state, which is the resource state, and then you just do local measurements on it sequentially, and which measurements you do depend on the computation you want to compute. Already 2005 or so, Ignacio and Frank showed that this cluster state is a PEPS, is a 2D PEPS. And indeed, they managed to interpret this measurement-based quantum computation in a very nice way, because once you do the measurements physically, these measurements will implement in the virtual degree of freedom a quantum computation. So by doing the measurements here, these measurements induce gates in the virtual degree of freedom. And now the virtual degree of freedom are the qubits in which and how this quantum computation is effectively doing a circuit model. And in this way, the PEPS made a nice correspondence between measurement-based quantum computation and circuit model, because this measurement-based computation is just nothing but the circuit model in the virtual degree of freedom. And this allowed to create new resources beyond the cluster state for measurement-based quantum computation. What else? For instance, quantum cellular automata are related also to, for instance, in 1D at least, exactly the same indeed, of matrix product unitaries, which are matrix product operators, which are unitary operators. And by exploiting this correspondence, we managed to reprove and characterize what is called the index theorem for quantum cellular automata, just by exploiting properties of the matrix product unitary operators. What else? Okay, it's just 2 minutes, so let me just, what else I wanted to say? Something interesting. I mean, quantum circuits are a subfamily of tensor networks. If you see the circuit graphically, you can see that it's a tensor network. And then tensor networks methods have been used to simulate quantum circuits, but also to construct explicit examples of states which require exponential depth to be constructed. I mean, and this is this very nice result of Jia and Wolf, in which they exploit, again, the tensor network description of the circuits. Okay, I commented already about holography, but very briefly, but I guess there will be other talks about this, in the sense that these toy models for holography are just PEPs if we see the PEPs as a boundary to bulk correspondence, and all the tensors are perfect, meaning that they define isometries in all possible combination of legs. And this gives an isometry from bulk to boundary that fulfill nice properties like the Ryuta-Kayanagi formula, etc. And let me just finally comment on something which somehow is related also to computing, but to classical computing, which is these connections to the complexity of matrix multiplication. Because indeed this is related to understanding a very particular matrix product state of 3 legs, sorry, of 3 sides, which is what is called the matrix multiplication tensor, which is the simplest matrix product state, which is just pairs of maximal entangled state between neighbors. And understanding at which rate I can interconvert with some errors between copies of this state and copies of the GSC state, this is somehow related to the, which is the optimal exponent in the complexity of doing matrix multiplication. And again, exploiting the connection with quantum information, there have been some nice recent results led by the group of Mathian Christandels and others in particular, I think, people from here. Okay, I think that's probably time to stop. Okay, thank you very much for your attention.
Time for questions?
Can you say again the result about circuits of exponential depth? What is the result?
The result is there is a explicit example of a state that I don't know by heart, but I can look for it and tell to you. So that if you want to construct this exactly, you need, with a quantum circuit, the circuit must be of exponential depth. Explicit, yeah.
Such things in circuit.
Okay, yes. Okay, I can, yeah. Okay, all I can do is just to look for the reference and tell you exactly which. I think it's really explicit. I mean, it's why the fact that you can write down the coefficients? Why does this imply?
Not if you have any explicit function that requires even exponential type, not just exponential depth. Then you have separate.
Then they have to.
There's still numbers. Complex. Well, you can just transcendental the numbers and stuff at the end.
If you can, for circuits. That's not explicit.
I think it involves these kind of things.
Yeah, if you're in
it's not fully explicit. If you believe in transcendental numbers.
If you allow.
I think that's what I.
Okay. I can for the reference and tell you, and then we can see.
Your example about quantum computing and the lifetime of quantum memories, how does the noise, assumptions about the noise translate into the...
Yes. The noise model using is the Davis generator. So essentially, is you assume that there is a local thermal bath in the weak coupling limit, and then the noise is simply some Lindbladian operator that depends on the temperature. And this Lindbladian operator is local, and this is true for the Davis generator if the topological memory is an RG fixed point, so it's made of commuting terms, and has a quantum detail balance, local detail balance, meaning that essentially it's like a frustration-free, if you want, again. But which are two properties that one can prove for this is kind of the weak coupling limit. Defined by Davis, so rigorously. But the properties that we require from here is that this is local, meaning finite range, and is some sort of frustration-free in the sense that, I mean, in a finite region, this Lindbladian annihilates the thermal state. These are and then this is noise model. So it's a Markovian noise model. And then one can prove that the gap of this Lindbladian generator is up to constant the gap of the parent Hamiltonian of the thermophile double, which is the purified version of the Gibbs state.
So when you say the thermophile double, there is a Hamiltonian in the definition of the thermophile.
Sure. Yes. But this is another Hamiltonian. So the thermophile double is associated to the Hamiltonian of the topological memory. Once you write the thermophile double, this is a PEPS. And now this PEPS has a parent Hamiltonian that has nothing to do with the original Hamiltonian. It's the one of the original Hamiltonian. Yes. So
we are at finite temperature, and then there is a noise model that
exactly.
tell us what the strength of the parent Hamiltonian is. There is a coefficient.
Exactly. But again, yes, of course. The coefficient is the temperature, but again, this is we prove this for fixed temperature. So of course the gap of this depends on the temperature, but for every fixed temperature, this Lindbladian has a gap, and therefore this converges fast to the thermal state. And in the thermal state, the information in the memory is lost because all the ground states have equal weight superposition. But yeah, there are two different Hamiltonians. One is the one of the topological memory. This is the one that enters in the thermophile double. So this is e to the minus beta h topological one. But now the parent Hamiltonian is the parent Hamiltonian of the purification of that. It's a different Hamiltonian. And this is the one, the gap of that is the one that corresponds to the gap of that. Yes.
So you mentioned chiral states, so we know there's this tension between PEPs and chiral states. I don't know, do you have some intuition for that, or for instance, can one generalize, are there states in 3 dimensions, for example, that are truly intrinsically 3-dimensional, which they could be cap phases in 3D, but they have no PEPs in a similar way?
That's a good question. No, I don't have any intuition at all on that. So all things that but probably you know much better than I do anyhow. So these recent ideas of going to mixed states, of course, these mixed states could be boundary of because if you go to mixed states, you can kill somehow part of the anions so that you are no longer in a double model, and then of course you could have things which are chiral, and then whether I think this is a nice way to go. And of course, maybe you can see these things as boundaries of higher dimensional models. But beyond that, the standard approach, of course, Ignacio can say much more than I on that. I don't have any feeling.
Yes, I think we'll stop here. Let me remind you that after the coffee break, we have discussions in 3 groups, so we can continue discussion there. So thank you.